So, in a real world, large-scale systems, consistency trade-offs, scalability limits as a real example of the requests like the very high read request traffic or very high write request traffic, a single database is no longer enough. At this point, we can already predict that if the load cannot be handled by one node and vertical scaling is no longer enough efficient in that case. So we need to horizontal scaling solution where sharding becomes irrelevant. So sharding can help with optimized scalability with distributing data. It is a horizontal database partitioning techniques that split large database into smaller, faster, and more manageable parts called shards. Not shards, just the shards. So it distributed them across multiple servers. Like its techniques were, firstly, we need to split our data into small parts, like we see in here, and store each part of these different servers. This is the main techniques of the sharding. So there are three main types of the sharding techniques, which are horizontal, vertical, and hybrid. So horizontal scaling. Horizontal sharding scale distribute rows of the database table. It splits the data row-wise version. It means the shard has the same schema but different subset of the rows. For example, we have, let's imagine 40 million of the user rows in our data table. We want to distribute it with the horizontal sharding techniques. We can split that 1 million for each our shard nodes. Like it means we have 4 shards and we can split into them. Each of the shards we can divide into 1 million users. Like first shard, we can store the user's ID from 1 to 1 million, for example. And from the second shard, we can store the 1 million 1 to 2 million. And so on, like the 2 million 1 to 3 million, 3 million 1 to 4 million database user IDs. So structurally, all shards look the same, but the data is distributed. When do we use the horizontal sharding? When our dataset is very, very large, of course, this is the important part, over the million of the users, for instance. And when we have a high read and write requests. There are some challenges of the horizontal scaling, of course, which are cross-shard queries like the joins. It means this part of this joins are difficult, it means, because the data is distributed across multiple shards. So the system has to fetch data from the different nodes and combine it over the network instead of the doing locally. That's why. And the next challenge is rebalancing data complex. It means that we need to move large amounts of the leave data between shards without downtime. Of course, while keeping consistency in updating routing logic. There, like the communication needs to be live, real lifetime. So this is the main advantages and disadvantages of the horizontal sharding. The next one is vertical sharding. Here, instead of splitting rows, we split by columns, of course, and features. That means one DB handles user authentication, for example. Another handles, for example, its profiles, and another can handle payments. So each shard has a different schemas focused on a specific function based. When do we use the vertical sharding? When different parts of the system have different access patterns, of course, and often used microservices techniques. So its challenges are firstly it requires join across the servers, of course. The second name is the network calls, because related data is split across different services. So combining it requires multiple network requests inside of a single local query. And the next one is more complex system design, because the system is divided into multiple dependent servers. And here we can see this is just a simple version, but as the logic expand, of course the scaling also will be expand. So each needing its own logic, database and communication layer, of course. And the next challenge is data duplication can be happen. It means some data must be copied across the services to reduce dependency and avoid frequent cross-service calls, of course. This is the main description of the vertical sharding. So the last main part of the sharding technique is hybrid sharding. So hybrid sharding is a combination of the both sharding techniques, which are horizontal plus vertical. In this approach, first we split the system vertical into servers in here, and then inside each server we can apply horizontal scaling. For instance, for example, in the user service we partition user by user ID. In the order service we partition orders by order ID, and each shard handles partition of the total traffic. It effectively, we now have two layers of the partitioning. At the top level separating by domain, which is vertical, and then the lower level distributing data with the horizontal table. This is what we call it hybrid sharding. So the advantages of the hybrid sharding is it can do maximum scalability, and it is a flexible architecture, of course, and optimized both reads and writes. There is some challenges of that types of techniques, of course, which are high operational complexity, because it combines both vertical and horizontal sharding. So we have to manage multiple servers, multiple shards at the same time, like here and in here. And of course harder to debug and maintaining, because the single request may pass through the multiple servers and the shards. It makes, of course, difficult to trace issues and ensure consistency, of course. So sharding was mainly about scaling the system by distributed data in many cases. It helps a lot of handling large volumes of mainly read requests, of course. But now another problem appears, of course. When the system grows even further, we start facing challenges not only with the reads, but also with data availability, fault tolerance, and write reliability. Because in a sharded system, each shard is still single point of the failure. So if one shard goes down, part of the system becomes also unavailable. And this is where the next technique is replication comes in. Replication means storing copies of the same data on a multiple nodes. So instead of having just the one copy of the data, we now have primary node and another separate secondary nodes. Another name is followers or replicas. The primary handles writes, and replicas receive updates and serve reads. Why do we need the replication? Of course, it is a high availability, means that if the one node fails, another replica can take over, of course. And the next one is read scalability, which means read requests can be distributed across the replicas. And of course, fault tolerance. Data is not lost if a machine crashes, even if the machine crashes, of course. So what else? There are three main of the different approaches of the replication, as looks like a sharding, which are single leader, multi-leader, and leaderless techniques. Firstly, single leader replication. So single leader replication, we have one node, call it leader, and all the other nodes are the followers. All write operations go only the leader, and whenever the user creates or updates the data, that request is handled by the leader firstly. After that, the leader propagates to the changes to the follower nodes. For instance, in a system like Instagram, when we upload any kind of our story or the post, that's a write operation, as we know. It goes to the leader firstly. But when thousands of the users viewing that posts, it means that the read operation happens. Those reads can be distributed across the replicas. This makes the system efficient for read-heavy workloads. This is the main advantages of the single leader replication. However, there's a limitation. If the leader loader fails, the system needs to elect the new leader. And during that time, writes may be temporarily unavailable, and also sometimes replicas can be lag behind. Lag means users might read slightly outdated data or old version of the data. Now, moving on to the next type of the replication type. This is a main advantage and disadvantage points of the single leader replication. The next one is multi-leader. Multi-leader replication. In this model, instead of having just one leader, we have multiple nodes that can accept write operations, both of them. So now users can write different nodes, often based on the geographic location. Imagine we have a, for example, global system where users in the, for example, European connects, European server, and the users, for example, in the US connect to the United States server. Both servers accept, for example, writes independently and later synchronize with each other. No? A good example of this kind of behavior can be seen in the systems like Google products, like the Google Docs, like as we usually call it, the Word, Google Words, Microsoft Words, we can say. Google Words, or for example, Google Sheets. Let's example of the Google Docs, where multiple users can edit the same documents, working the same document, and they edit the same, for example, part of the document. For instance, two users update the same field at the same time from different regions. The system has to decide which version is correct or how to merge them. So while the multi-leader replication improves write performance and availability, it makes a consistency much harder to manage. This is the main cases, this is the main challenges of the multi-leader replication's simple case. But this introduces a serious challenge. It means conflicts. For instance, if two users update the same field at the same time from the different regions, the system has to decide in which version is correct or how to merge them. This is a little serious or little challengeable things of the multi-leader replications technique. So, while multi-leader replication improves write performance and availability, it makes consistency much harder to manage. So, and then finally, we have leaderless replication. Leaderless replica. So, in these approaches, there is no any leader at all. Any node in the system can accept both reads and writes, of course. So, instead of relying on a single resource of single source of the truth, the system uses something called a quorum mechanism, which is, for instance, let's imagine we have 3 nodes, and the system might require that write must be stored in at least 2 nodes, like write happened and committed, and for example in the 3rd node it didn't. A read must also check at least 2 nodes, at least 2 of the 3. This is called query mechanism, that even if some nodes are outdated or unavailable, the system can still return correct data. But again, there is a little bit trade-off, but the correct data we have. This way, even if some node is outdated or unavailable, the system can still return correct data. Data is often not eventual consistency, meaning that different nodes might temporarily have different values, and the system needs to resolve these different later. It means consistency and availability important than consistency. So all in all, we saw the single leader means that, as an simple example, the replication gives us simplicity and strong control over write operations. Multi-leader improves the write availability across regions, different regions and different locations, and leaderless application gives us maximum availability of fault tolerance. So when we can use which techniques? When we need strong consistency and just a simple write operations control, we can use simple leader replication. For example, TikTok or any types of the web apps like this, social reels of the platform, where users are constantly reading the data, like the scrolling feeds, viewing profiles, while writes are relatively less frequent. It means read rather than write. In no write conflicts, predictable behavior. And when systems users are globally distributed and we want to low latency writes everywhere, we can use multi-leader replication approach. For instance, tools like the Google Docs, as we give the example before, Sheets international shareable products, like multiple users are editing the same document from the different locations. So the systems are availability is critical. It must never go down for fault tolerance or the partitioning. Of course, and tolerant eventual consistency, we can use leaderless application. It is more important to always accept writes than to guarantee immediately consistency. This is the main concepts of the types of the replication and sharding.